Well, you know, I was trying to think about how do you introduce somebody you've known for many years, and you know, if you go to a corporate website, the first things you'll see are the corporation saying they are the world leader in X, Y, or Z. But if you go to the websites of great people, you almost never see that. And you know, you see they've done this, that, and the other thing. But in fact, Mark and his wife Barbara Erickson, and I think it's reasonable to talk about both of you as a powerful force for good. Their website doesn't say that, but in fact they have been among the two or three groups of people that have been the most influential in trying to get education in general and computer education in particular to grow up. And they've done this both singly and together, traveling around. And last year they received the award, I think, that it ranks at the same level as some of the more familiar awards from the ACM, which is the Carl Karlstrom Computer Educator Award, won by people like Don Knuth, people who have put a lot of effort into not just trying to advance computing, but to put it in forms and help people understand what it is and spread it and improve it. And you know, we live in a society that tends to value things by money, and so we generally give short shrift to education no matter what we say about it. But on the other hand, I think anytime we have a great educator in our midst, we should be very thankful that they exist and welcome them wholeheartedly. Thanks, Mark.
There we go. Thank you so much, Alan. That was wonderful. Hi, everybody. It's great to see so many faces that it's been a long time. Hi, Don. I haven't seen it in a long time, and it's a real pleasure to be here. Thank you so much for the invitation. I want to talk about two of the C's in C5. I'm particularly interested on how we help people create with computing. And here's my story, and I'll give away all of my punchlines here. I argue that computing is important for everybody, not just for those who are going to become majors in computer science. And I'm going to tell a little historical story that tries to make the argument that it's our job as computer scientists, that it has been explicitly our job for 50-some years to teach everybody about computer science. And then I want to tell you three stories about trying to do that, about the issues involved in trying to teach computing to everybody, particularly trying to teach everybody at Georgia Tech, which includes the liberal arts, architecture, and business or management majors. The story number two about computer science. Story number two is the work of my former student Brian Dorn, who tried to teach graphics designers about programming. That's a little bit an odd way of putting it, and I'll explain that more later, but graphics designers today are teaching themselves to program because it turns out to be really useful to them. They're not doing a particularly good job of it, and I'll tell you more about that. And then finally, trying to understand the needs of high school teachers learning computer science. And this last one, which most directly connects to my wife Barbara Erickson's work, I'm not actually going to give you a lot of successes yet. We're still trying to understand the issues, and I'll mostly tell you about two studies and trying to understand those issues. So here's who we typically think of as the student who's going to take a computer science course, somebody who's going to grow up to be a future software engineer. What do we want them to learn? We want them to learn how to produce reliable, robust, secure software. We want them to have soft skills like being able to work in interdisciplinary teams. We want them to use appropriate design notations. We want them to be able to work in multiple programming languages. I think for those of you who teach computer science at the university level, you'd probably say, yeah, that's what I want for my students. This is a graph of participation in the advanced placement exam in various STEM disciplines. This very sharply moving one here, and I'll have to stop that. Let's see if I can make this work better. Yeah. This one here, that's calculus. Okay, here's biology. Those are the big two. Even a relatively newcomer like statistics is here. That's the blue line here. This really dismal line, that's computer science. Okay, that's the number of people taking advanced placement computer science over the since 1997. It's a really distressing thing to see that all of the other advanced placement exams in STEM are rising. And no matter how you feel about advanced placement, this is an indication of interest in the field. And interest in computer science is pretty dismal in high school. But what I want to argue is that that's not even part of the picture. That there's a lot of people who need computer science. Computer science is core to innovation in a lot of different disciplines. And there was a really interesting study that folks at Carnegie Mellon University did in 2005. Chris Scafidi, Mary Shaw, and Brad Myers. For the Department of Defense, they did an estimation of who was going to be doing the software in 2012, this year. And they argued that there would probably be about 3 million professional software developers right now, and about 13 million other people who code but are not professional software developers. 13 million is a really big number. So for every student in the computer science class hoping to become one of those future software engineers, there's another 4 elsewhere on campus who need what that computer science class is teaching about, but are unlikely to come into that computer science class. Who might those students grow up to be? Well, here's one, a future computational scientist or engineer. And the learning outcomes for them are markedly different than that for a computer scientist. They are going to use computation as a tool to enhance understanding. They have a relatively little interest in computation by itself. They're going to write relatively small programs. I work with a chemical engineer professor who does work in MATLAB. He promises that he codes every single day, typically about 10 lines of code. He says an enormous program for him is 100 lines of code, and if he followed the documentation standards that we require of all first-year students at Georgia Tech, he'd have to write an additional 15 lines of documentation for those 10 lines of MATLAB code. And he doesn't understand why. And I understand what he's saying. He doesn't typically write code for anybody else but himself. He typically throws away all of his code at the end of the day. If they want to produce something which is reliable, robust, they bring in the software engineers. They bring in professionals. But for the most part, that's not what they want to be doing. They also learn as few languages as needed for their tasks. They're not going to go out and learn Haskell or OCaml just because it's the cool new language of the day. That's not what they're interested in. Here's another atypical computer science student that everybody in this room should be really worried about. How do high school teachers learn about computer science? What are they learning about computer science? There are a lot of high school teachers who really do want to understand computer science in order to teach it well. They are not interested in programming for programming's sake. They want to use code to explore and understand ideas of computation. They will learn whatever languages they need to for their students' sake, but they're not particularly interested in learning new languages on their own. These are folks who are going to work with students with a wide range of interests, but some of these folks may never even meet a professional software engineer. The pictures here are from some of Barbara's workshops that she does with high school teachers. The chroma key in the corner, the teachers have to write the code for the chroma key, so they put themselves on the brick wall. Oops. And then I want to tell you a little bit about graphics designers. Graphics designers today are teaching themselves how to code, either to put things up on the web or because they use Photoshop or GIMP, both of which are scriptable. And for a lot of graphics designers who are freelance consultants, time is quite literally money. So if you can automate something, if you can batch process something, you are literally making yourself money. And so there's a bunch of them that are teaching themselves how to code. They want to do as little coding as possible. And they want to learn about computing ideas in order to improve their process, but with a focus on people and creativity. And that's not what they think computer scientists are about. And we'll talk more about that in a little bit. And these are folks who probably won't ever work with professional software engineers. And I'll give you examples of those too. The images here are from a graphics designer's programmer's website. This is their own self-depictions of how they see themselves at this website. So how do we meet this need for teaching computer science to absolutely everybody? Our track record for intro computer science courses around the world is relatively poor. 30 to 50% failure rates are not uncommon in the first course. And that's with people who want to become professional software engineers. Other majors tend to be much more ethnically diverse than the typical computing student, more female than the typical computing student. And our track record with those audiences is also really poor. So, okay, big problems, Mark. But is it our job? Do we really have to deal with this? And do all those folks want computer science? In 1961, MIT Sloan School had a symposium on computers and the world of the future. This is my scan of my used copy of the book. It's way out of print, and it's really hard to get copies of these days. But it's a wonderful book because it not only includes all of the lectures, but also transcription of all the discussions that went on. And this symposium was a who's who of computer science in 1961. I want to talk about two of the lectures in this chapter. One is from Sir C.P. Snow, and I'll say more about C.P. Snow in a little bit. One of his discussants was Norbert Wiener. People know the name Norbert Wiener in here? Ooh, I figured this would be an audience that would know more of these names. This is the person who invented the term cybernetics and literally wrote the book. The other speaker that I want to talk about is Alan Perlis, one of the first winners of the ACM Turing Award, our Nobel Prize of Computer Science, that Alan is also a winner of. Two of his discussants were Peter Elias, who was the head of electrical engineering at MIT at the time, and J.C.R. Licklider. Okay, another show of hands. How many people know who J.C.R. Licklider is? About the same people, I think, both times.
This is also important because this is right before Lick got the money from ARPA.
Right. So J.C.R. Licklider, so whether or not you believe that Vint Cerf or Al Gore was the father of the internet, it's clear that J.C.R. Licklider was the grandfather of the internet. He's the one who funded the original nodes to make it all happen. So let me talk about Alan Perlis's talk first. He talked about what was going on at Carnegie Tech at the time, where they were explicitly creating computer science for everybody. And he argued that everyone on campuses today should be taking a course in computer science, and they should all be learning to program, that we should think of computer science as part of a liberal education. Why? He gave two arguments. The first was that computer science is the study of process, and he contrasted it with calculus. Calculus is the study of rates, and rates are really important in a lot of different fields, from physics to business. Computer science is the study of process, and everybody cares about process. When I teach my management students and I say that, by the way, computer scientists know how to prove whether or not an algorithm is correct, the students who care about logistics' jaws drop. You can prove something about process? And this notion about being able to compare processes and talk about which ones are effective or ineffective and which ones are fast and how much memory they're going to, these are things that they just haven't even thought about a lot. The second part is that automated execution of process changes everything, including how we think about things we already know. Perlis argued that once you know loops, you can't think about integral calculus in the same way again. Because the whole notion about delta x and the limit as delta x goes to 0 is just a kind of a loop. And it changes the way that you think about things. And this is an amazing lecture in being so prescient about computational science and engineering. That was essentially what he was pointing to, that when you have computation, when you can take the processes, how you model things in science and mathematics and engineering, and put them in the computer and simulating them, and that changes everything. He was absolutely right. Now, there was pushback. Elias, in particular, thought nobody should learn how to program because eventually that'll be taken care of for us. They should be ingenious enough to do it without the human symbiote being obliged to perform the mechanical chores of learning to program. Licklider was one of the responses to that, and he said, I'll bet you when the first apes were trying to talk, they thought this learning language was an awful bore. Do we really have to go to all that much trouble? And yet, today we have poetry. Perlis actually made a different kind of an argument back. He said, what we really want students to understand is about process, and understand about how complex processes are made out of simpler ones. And the best way of teaching that important big idea is with having them learn how to program. C.P. Snow famously wrote the book, The Two Cultures. And when I was a graduate student, my advisor, Elliot Soloway, made all of his students read this book. C.P. Snow, you may be aware, was a scientific advisor to the United Kingdom during World War II. And Two Cultures was his concern, was based on his concern that the Western world was splitting into two halves. A half that cared about science, that we now think of as STEM, science, technology, engineering, and mathematics, and a half that cares mostly about humanities. Now, C.P. Snow put the blame for this split on the humanities, that it was all their fault, that humanities thought of science as being yet another way of coming to know, as opposed to one that is particularly privileged because it's based on evidence in the scientific method. Not trying to get into that argument. Why did Eliot make all of his students read this? To think about the students who don't come into your classes and how you might reach them and what it is that they value. And now if you think, well, oh, this is 50 years, you know, we don't have this split anymore. You might have heard about this book, Denialism, and talk about the folks who still today don't recognize the value of science. Rick Perry tells us that evolution didn't really happen. We know from a lot of folks that the climate isn't warming, and you probably should avoid vaccines. That's a good point. We could raise that issue as well. So C.P. Snow's chapter was actually very similar sort of a stick to Alan Perlis's carrot. Alan Perlis is saying if you have learning how to program, you have a carrot. You have a very powerful tool at your disposal. In 2007, The Economist had a piece about the algorithms that control our lives yet we don't understand. One might argue that the mortgage crisis was caused by people who didn't really understand the algorithm of adjustable rate mortgages. And C.P. Snow foresaw this in his piece in 1961. He argued that those who don't understand algorithms can't understand how these kinds of decisions are being made. And a quote from his chapter, "A handful of people having no relation to the will of society, having no communication with the rest of society, will be taking decisions in secret which are going to affect our lives in the deepest sense." Which is, again, a pretty prescient chapter. So, I've tried to argue that historically this has been our challenge. So, how do we meet this challenge? Let me talk about 3 different audiences, briefly, about how we can try to teach computing to absolutely everybody. And the first one is about the story of computing for all at Georgia Tech. Oh, I wanted to tell one other brief thing. Do they want what we have to tell them? This is a wonderful quote from Richard Dawkins. In April 2007, when he was talking about his, at that time, latest book. And Terry Gross asked him, how is evolutionary biology in a really wonderful place today, which is one of the things he said in his book. And Dawkins says, since Watson and Crick in 1953, biology has become a sort of branch of computer science. All the familiar metaphors from computer science fit. So here we have arguably the most famous biologist in the world essentially ceding his field to computer science. Yes, they do need what we have to tell them about. So, story number 1, teaching computing to everybody. In fall 1999, a decision was made by, well, actually, it was implemented in fall 1999. A decision was made earlier by the faculty that all students who come to Georgia Tech must take a course in computer science. The defined objectives for the course are really pretty rigorous. Everybody who walks in the door must be, who takes this class has to be able to write programs where they make both algorithmic and data structure choices in the first semester, which means that things that you're learning, you have to learn at least 2 ways of doing them so that you can make a choice between them. This is already a pretty hard first semester course. And so it's considered part of general education that everybody has to take it. From 1999 to 2003, we used an approach that Russ Shackelford promoted with using pseudocode, not actually an executable language. We later moved to Scheme using the How to Design Programs approach from MIT Press. This is data on the last 3 semesters that we taught computer science to absolutely everybody. I know you can't see the details here. Let me try to fill it in for you. This is everybody, total. This is females, males, for the last 3 semesters. Red is students who withdrew from the class or received a failing grade in the class. And blue is those who passed the class. What you can tell immediately is there's too much red. What you can also see is that the women are failing at nearly twice the rate as the men in this class. Okay? Now this is absolutely everybody. So this includes people who do want to grow up to be software engineers. This includes people who want to grow up to be scientists or engineers. How about the folks who you wouldn't typically think would want to take a computer science course? Those students were not doing particularly well. Students in architecture, liberal arts, and management majors were failing the class at more than 50%. Now overall the class had a 78% success rate, which is a really pretty good success rate for CS1, but that's considering everybody. These majors were not doing so hot. What's going on? Now at about the same time as we were struggling with this, a number of really great reports talking about what was going on with computer science curricula were coming out. The best of these is probably Unlocking the Clubhouse, Women in Computing at Carnegie Mellon University from Jane Margolis and Alan Fisher. But other good reports came from the American Association of University Women and the American Association for the Advancement of Science. All of them say that that students perceive computing as being tedious, boring, and irrelevant. Okay, for anybody who's programmed, which I'm going to guess is 99% of the people in this room, you can understand the computer science sometimes being tedious, and even sometimes boring. But irrelevant? how could computer science be irrelevant to these students today? I mean, they've got computing everywhere. If the students come into that intro course, most often, and at most universities, it's because they think that things like laptops are really cool, and the tablets are really cool, and the Wii controllers and Kinect, those are all really amazing things. But think about those students who are really excited about all that technology. They come into that intro course and we say to them, hey, would you like to solve the Tower of Hanoi? I bet you don't know what the next Fibonacci number in the sequence is. The students don't see a connection between what it is that we're telling them in the computer science course and what brought them to computer science in the first place. So since spring 2003, Georgia Tech teaches 3 different introductory computer science courses. We're explicitly following a recommendation of Margolis and Fisher to create alternative paths into computer science, different kinds of introduction to computer science. And each course introduces computing using a particular context, an application area that pervades all the examples, all the homework assignments, all the lecture discussion. We're explicitly about trying to teach computing in the ways that the students see as being relevant. Oops. So at Georgia Tech, we now have 3 different CS1s. The first one, which is a continuation of the one that used to be the one course for absolutely everybody on campus, now uses robots. The second course is for engineers. It's a very similar topic, but it uses MATLAB, and all of the problems in the course are engineering problems. We literally have all the engineering faculty submit problems that get used in this course. And then I get the last one. I get all the management, architecture, and liberal arts majors. And I teach them media computation, which is, the topics are not dissimilar from a CS1 course, a typical computer science introductory course, but they're all about manipulating multiple media. In every intro computer science course, you do something with all of the elements of some data collection. So typically you're going to compute the average or find the maximum value in an array. We do the same thing, except we're going to compute the grayscale of an image or create the negative of an image. In every computer science class, you do something with only part of the array, only part of the data structure. We do the same thing by removing red eye just around the eyes without touching any other red that the person might be wearing. We get to talk about algorithms. So it turns out the algorithm by which you have some transparency on one picture, you can see the other one, is exactly the same sort of weighted sums by which you have one sound fade out. Well, another sound fades in. Exactly the same kind of an algorithm. We have a data structures course in media computation now where well, we manipulate linked lists. Every data structures course in the world has some sort of an assignment where take some piece of data, make umpteen copies of that data in the linked list, take another piece of data, make more nodes of that one, interleave it between the other ones, and then another piece of data, we skip every other node, something like that. And when these nodes contain things like numbers or strings, this is among the world's most boring programming assignments. But when these nodes contain MIDI notes, you're actually doing Western music composition. Okay, you can actually think about having different motifs appear and recapitulating different motifs and weaving in the different kinds of ideas. We also get to touch on really big ideas of computer science that you rarely get to in the introductory course. The image in the lower right-hand corner is taking the sound for the words, "This is a test," and matching each sample of the sound to one pixel, and then picking the color of that pixel dependent on how big or small the sample is. Okay? This is now a visualization of that sound. The really cool part is where you write another program that knows about the mapping, takes the picture in as input, and gives you the sound back again. That was a sound that came out of a picture. For all the students who were actually paying attention and doing Facebook at the time, the back of their heads blow out, right? Because now we're talking about information in the Claude Shannon sense, in the sense of being apart from any particular medium, and that could be mapped to any medium to show you different things or for visualization or to hear different things at normalization. So this is the sort of code that we talk about in the first few weeks of the class. Here's Santa Claus. We're going to remove the red from Santa Claus by writing in Python for pixel and get pixels of the picture, set the red channel of that pixel to 0. We compute the grayscale by simply taking an average of the red, green, and blue, which is a reasonable stand-in for luminance. And then we get the negative by simply computing the inverse. Since the value of red, green, and blue is between 0 and 255, 255 minus that is the negative of that, and that gives us the dark elf or goth Santa look. One of the really cool things about this class is that I specify in programming assignments the computation that I want students to do, but I don't particularly care what they do it with. So I might ask them to build me a collage where the same picture appears multiple times, but doing some manipulation to it on those multiple times, and then mirror the whole canvas to give us a nice look to it too. That's where these two images come from. We also do similar things with movies, where I want them to build a movie where I want at least 2 things moving at once and make it about 5 seconds long, and I don't really care what's in the picture. We do similar things with sound. And this last one, this is a linked list. It's pretty natural to map it to a linked list. This is the next 3 semesters after we started with media computation. And what you can immediately see is that the women are now doing better than the men in the class. There's a lot less red, but that's still, we're doing an apples to oranges comparison. The previous course was absolutely everybody on campus. This is just the liberal arts, architecture, and management majors. And so if we look at those individual majors, we see a pretty remarkable rise in terms of the success rates. These students are sticking it out in the class. Okay? Now, what I'm hoping that some of you who think really hard about education are saying to yourselves is, but are they learning the same? Well, I do suggest to you that those who finish all 15 weeks learn more than the people who dropped at week 5. But nonetheless, it's a valid question that I don't have a good answer for yet, but you can bring it up later and I'll tell you some about our research in that area. Was the class successful? During the first semester, we did a lot of interviews with students and we got a bunch of quotes. I didn't get to see any of them because I was teaching the class. So on the last day, Andrea Forte, who's now a professor at Drexel, she ran the evaluation study and she dropped all these interviews on my desk, and this was still my favorite to this day. I just wish I had more time to play around with that and make neat effects. But Jess, the IDE we use in the class, will be on my computer forever. So that's the nice thing about this class, is you can go as deep into the homework as you wanted. So I turned in that me and my roommate would do more after to see what we could do with it. This is a female liberal arts major admitting to coding outside the requirements of the class, and glad that she can code after the class ends. A year after the class finished, we went back and tried to track down all the people who had taken it that we could, and found out that 19% of the students had programmed since the class had ended. No other computer science classes, and these are liberal arts, architecture, and management majors, but they'd found something useful to code. Did the class change how you interact with computers? Students told us things like, definitely makes me think about what is going on behind the scenes of such programs like Photoshop and Illustrator. Yes, that's what you want. You want the students to be thinking about where is their computation coming from? How does it work? Other schools have adopted media computation, and we've worked closely with Gainesville College in the North Georgia Mountains and University of Illinois, Chicago in their assessment. And what we find is that we have a similar increase in success rates at both the University of Illinois, Chicago and at Gainesville College. An interesting question. We asked the students afterward, at both Gainesville and Georgia Tech, we used the exact same surveys for multiple semesters. Would you like, after this class, to take more computer science? At Georgia Tech, 15.2% of the students strongly disagreed, which is colloquially, hell no. Less than 25% of the students agreed with that statement. But would you like more media computation? Both Georgia Tech and Gainesville students, over 40%, agreed with that statement. At the University of California, San Diego, they now teach media computation for the first quarter course to absolutely everybody on campus, to all the CS majors rather. Okay, so for just CS majors, first quarter, and that's the only class that they changed. And Beth Seidman, who is sort of the Energizer Bunny of CS education research, she's produced more prolific than anybody else. She's been running the evaluation study there, and she took a lot of data from the last cohort before they did media computation and has followed them up since then, and found that the media computation students have higher pass rates and retention rates 1 year later without taking any other class, which is one indication that they are learning the same, that they're doing well in the succeeding classes despite not having any other differences. I mentioned that we also have this MATLAB course. The engineering students as well, their pass rate improved. Among our 3 CS1s, the 3 different introductory courses that we teach, these are the first students to program outside of course, outside of the class. Any ideas? Why would a MATLAB student in engineering want to program outside of the class right away? Yes? Agreed. But think about the classes that an intro computer science, that a engineering student is taking in their first year. Any guesses, people who know MATLAB? Multivariate calculus. MATLAB has wonderful visualizations. And almost all of the students, they figured out without, nobody got prompted. They just started whispering to one another, "You can see what it looks like." Because they could see what their equations looked like where they hadn't been able to previously. In spring 2004, this is the pass rate and success rate of all three of our CS1s. This is the one for engineers. It's about 1,200 students a semester. Media computation is about 300 students a semester. CS for CS majors, 150 students a semester. It's quite literally true in that semester that the non-majors were more likely to pass computer science than the CS majors were. And it was at this point that we realized that even the CS majors, they didn't care about the Fibonacci sequence either. So this is where we started teaching robotics in the introductory computer science course. I have not only been peripherally involved in the project as the evaluation person. The leads are Tucker Balch, Deepak Kumar, and Doug Blank. They work on wonderful assignments in this class. So for example, the lower right-hand corner, it may not be visible to you. Those are robots with costumes on. And they do plays. And they also make movies. The camera, you can see in the upper right-hand corner, that's the Scribbler robot with the little dongle that Tucker Balch's group created that has a camera on it. So they can take scenes quick enough that they could actually have one robot be the cameraman just by taking a lot of stills. And then afterward, they might do media computation to create blurs or background subtraction or chroma key. The really cool thing that I like about this particular assignment is that not only is it creative, not only is it collaborative, but it's also actually a programming assignment on parallel programming in the first course while in Python. How does an actor know when it's their cue? How does the cameraman know that it's time to pan? The students have to actually work out all the timing with one another, which is getting them thinking about those sorts of issues. Story number 2, graphics designers who program. So Brian Dorn finished his dissertation last August 2010, and he studied graphics designers who program. For the most part, these are folks who have not taken a lot of computer science previously, and they don't value it very much. As one participant said, so that was a really long way of saying, yes, I think that an academic study of computer science would make me a better programmer, but not by a whole lot. Now, Brian studied these folks in a lot of different ways. He found that most of the people that he studied who took his surveys were arts and media trained. They don't consider themselves a programmer. 83.3% say, no, I am not a programmer. Only a little less than 40% have ever had any formal training in computer science. And even those who did, they don't necessarily like it. But if you could see from some of these, I know it's fairly hard to see, they're actually doing a lot of different kinds of programming in their work in graphics design. Where are they getting their CS knowledge? Mostly online, FAQs, books when applicable, but there's very few books that say ActionScript for graphics designers. They don't find books that are really aimed at them so much. They don't rely on classes very much. All right, so these, I want you to preface these quotes because what makes them very scary is that these are not undergraduate students. These are adults, 25 to 40 years old. Okay? What do they think that software engineers do? Boring stuff. Well, you're going to be front-end. You're not going to be front-end anything with computer science. You're going to be back-end everything. And they're programming something, and they don't really see what it's going to look like. They're just making it work. Who is in computer science? What's really amazing is that Amy Bruckman and Sarita Yardi did a study in 2007 of what preteen girls think of computer science. And what these adults say is shockingly similar. And they were old, and they were nerdy, and they were boring. They enjoy seeing them type up all these numbers and stuff and what it makes things do. Okay? I would suggest that graphic designers are unlikely to seek out a software engineer to work with. Why don't they take computer science classes? Well, I started out in computer science, but I didn't like it at all. So you weren't really learning any concepts. You were learning the languages, and I didn't like that at all. So that's why I left. I think this is a really compelling quote for those of us who are teaching computer science to think about. Every time that I've visited a school and talked to their curriculum designers, I've met with a whole bunch of curriculum designers, they tell me all about, well, we have this class which is about data structures, and this class which is about parallel programming, and this class which is about functional ideas. And then you go talk to the students and you talk to the same people around coffee and let's say, well, that's my Java course, and that's my C course, and that's my Scheme course. All right? Do we really teach the concepts, or are we really teaching the programming languages? Now, also when I tell these stories, a lot of computer scientists say, well, those graphic designers, they don't really want to code. What interests you about coding? The coding. I don't like to code. Because, I mean, the code is just, there's so much you can do with code and stuff, it's just like, wow. Don't you want all of your undergrads to say this in computer science? And these are graphics designers. They see the value of what they can do with code. They want to know more. In particular, they want to know more than just the details. Like, what do I want to learn? Like computer science, theory. I want to read a book on design patterns. I want to keep doing that because it made me a better programmer. It was more fun to program. It was more thought-provoking. The problem for these folks is that because they haven't had, for the most part, any initial knowledge, they get lost. So Brian did a lot of observations of people as they're working on various tasks. He gives somebody a piece of code, and they see the variable foo, so they type into Google JavaScript foo. And shockingly, nothing useful comes up. They don't know to look at, say, API names versus just a normal variable name. They don't recognize those as being different or significant in any real way. One time, Brian gave somebody a task, and they accidentally landed on a Java page and sat there for a half an hour before he pointed out to them, you're programming in JavaScript. That's not going to help you. How much time might they have wasted had Brian not been there to stop them? So what Brian's experiment was, it turns out these folks rely a lot on code repositories. There are a lot of code repositories for graphics designers who want to do X done. These people trust executable code. They rely on those code repositories a lot. Could you modify the code repository so that, by the way, it points out the computer science ideas? So that it might say to them, by the way, this is called an array, and this is a Boolean, and this is a definite loop. Because not knowing the language is a huge hindrance. If you're trying to understand a piece of code with try-catch in it, what you really want to know is the words exception handling. But how do you make that mapping? That's the sort of thing that he was trying to show them. And what he finds is that in general, cases work. Both groups, the people who get a code repository versus who get a case library that talks about how the computer science ideas in it, both groups like their repositories the same. They both code the same. They're able to accomplish the same tasks. But those who get the cases actually pass a test in computer science afterward. They've learned the concepts. And I think that Brian's work really points a way to think about how do we teach computer science to non-CS professionals who discover computing late in life. Story number 3, high school teachers need a new kind of pedagogy. For the most part, the way we teach computer science is a form of apprenticeship. And that makes a lot of sense for people who are going to grow up to be professional computer science software developers. We try to model things and lecture, we tell people about, but we expect that most of the real learning of computer science occurs in practice, spending time with the IDE. We try to coach them, but for the most part, we expect people to figure things out on their own programming. Practice is always important. Do we rely on it too much? I suggest that computer science, more than any other STEM field, requires a great deal of practice. We're more like architecture. Architects expect to spend a lot of time in studio in order to learn their practice. That's the way that we teach computer science. The challenge to that is that CS pedagogy is time-consuming. It requires a large investment of student time. That's a problem if what you're trying to teach computer science to are working high school teachers. So one of the big problems that we have in secondary computer science in the United States is a lack of teachers. So part of my effort, along with Barbara Erickson in Georgia, is to increase the number of high schools in Georgia that offer computer science and to have well-trained teachers in those classes. In Georgia, we are currently have the largest percentage of high schools in the Southeast offering advanced placement computer science, which is one way of measuring computer science in a school at all. And actually, these numbers have continued to drop. It's currently at 20%, and we lead in the Southeast. Why do we compare to the Southeast? I don't know. It's some sort of Civil War thing. But what's striking is what's going on in the other states. Alabama, which actually has a very comparable population in size to Georgia, has 14 teachers in the entire state. Okay? There is no computer science out there. So where are we going to get the teachers from? The National Science Foundation has a goal of having 10,000 high school computer science teachers by the year 2015. We have 2,000 today by measuring advanced placement computer science teachers. So one of my students, Li Jung Ni, just completed her thesis where she asked the questions, what makes a computer science high school teacher a computer science teacher? What makes a high school teacher say, I'm a computer science teacher? It's actually something that we want. A high school teacher who self-identifies as a particular kind. I'm a science teacher. I'm a reading teacher. I'm a history teacher. Those teachers are more likely to be retained. In general, we lose about 50% of all STEM high school teachers in the first 5 years. But if they identify as a science teacher, they're more likely to stay in the job. They're more likely to seek professional development. I want to become better at the kind of teacher that I am. They're more likely to join a professional community. Now, the number one way that a teacher has a sense of identity is the certificate that they have. I am certified to teach science. I am certified to teach math. Almost no state in the United States offers a certificate in computer science. You can't become certified to be a high school computer science teacher. You can sometimes get it in as an endorsement and add on to an additional certificate, as we have in Georgia, but there's very few states that have that either. So, people who are teaching computer science today, how do they identify themselves? What do they call themselves? And then how do they become computer science teachers? Those are the two questions that Li Jingni asked in her thesis. I'm going to talk about only the first one today, because that sort of sets up the problem. So these teachers who are teaching computer science today do feel a need for more training. It is hard for them. Most of the people who teach computer science today in high school have never had a computer science course. I mean, if they've worked through Barbara, they have taken a series of one-week summer workshops over multiple years. And that's better than nothing, but especially given the way that we teach computer science, that's a lot worse than taking a semester-long course. Most of these teachers tend to think of what they're teaching as math, even if they are business teachers. In most states in the union, computer science is considered a business topic. And so it's taught by business teachers, teachers who might also be teaching accounting or keyboarding skills or how to use Microsoft Office. I really think computer science is a math type course. It's like applied math. Another huge issue, another reason why these teachers see themselves as math teachers is because there is a community of math teachers. There's somebody to hang out with and talk to. The computer science teachers don't have a community to belong to. This is a particularly compelling quote for me. I won't read it to you. I'll have you take a look at it. This is a teacher who thinks that computer science is beyond her. She thinks she's capable of teaching how to use a computer, but not capable of teaching computer science. And this is somebody who is teaching computer science in Georgia. And this is really scary about what sort of messages she's sending to her students about the field of computer science. Now, so how do we teach working high school teachers? How do we reach them wherever they are and teach them something about computer science? Well, there are relatively few programs for high school teachers to learn about computer science. What we did to be able to model this is we went to Columbus State University, which is now offering online courses for high school teachers to learn computer science. And we studied some of the students who are taking those courses now. And what we find, these are all adult professional students, people who are working full-time at real jobs, trying to take computer science at a distance via online resources. And they don't have the time to spend hours in front of the IDE. What typically stymies them is because things happen in their lives. Right? These are working adults. Things happen, things with their work, things with their family, and then they can no longer handle the hours in front of the IDE. They also lack background in mathematics, and they get stymied by small errors. These are some of the quotes that Clara Bunda gathered. She's the one who did the study, working with Amy Bruckman and I at Georgia Tech. The last one I will read to you. There were times that it would take me hours to find one comma out of place, or find that one something that was wrong. So I didn't mind sticking with it, but it just got to the point where I just didn't get it. Could we teach more of computer science more efficiently? I mean, does it have to be involved with lots and lots of practice? We know what's going on when these folks are learning computer science. Matt Jaded has done some wonderful log file analysis and video stories about how, here's the classic one, a while loop and put a semicolon before the first curly brace opening the block. That's a half an hour. It always takes students a half an hour because the Java error messages are absolutely horrible. And it takes them a half an hour to figure out where that problem is. Could we teach about all of these things without that half hour of where does the semicolon go? Can we reduce the wasted time? Could we make computer science into something that people could study? I don't want to eliminate the practice, but I want the practice to be more effective. Here's an analogy. If you learn some coursework in a foreign language, does that help you to learn the language more than just being immersed in the language first? I suspect that some coursework, any coursework, helps you get started. That's where our new project is, CS Learning for You. I don't have any answers for you yet, but I'll tell you some of our thoughts at the Friday panel. So, conclusions. Computing is important to let everybody create, and it's the job of computer scientists to get it to everybody. Non-computer science majors tend to succeed with context. They want to see computer science in some application area that makes sense. Story number 2, end-user programmers want what computer science has to offer, and they don't know enough about computer science to teach themselves effectively. And story number 3 is that teachers want to know more about computer science. They want more training, but our existing pedagogical methods aren't going to work for these full-time working professionals. Lots of folks to thank. Most of our work is supported by the National Science Foundation. And here's some URLs and pictures of the books that Barbara and I have done. I'd be glad to take any questions. Thank you very much for your time. Alan.
So, sort of broadcast down this direction.
Please, yeah.
Yeah. So, one of the things that's always bothered me here, of course, Mark knows about pretty much every opinion I have. Put it on his blog. But to me, a lot of these people are simply exhibiting really good taste in the face of really stupid stuff in CS in general and in teaching CS in particular. They're basically, you know, just personally, I wouldn't blast through one of these courses because if you take what Perlis said, Perlis, by the way, made up the term computer science. That's what he meant. And if you take that it's supposed to have something to do with the study of process and take a look at what AP is about, they essentially almost don't overlap. And so CS today means, you know, I think 2% of stuff that's worthwhile learning in the first course, and the rest of it is a lot of mathematics and a lot of history that has nothing to do with what it means to be a learner. So that bothers me a lot. And teachers are in this terrible position where they don't know that their taste is discerning the truth. This is shit. That's what they're reacting to, but they feel inferior. Like this takes blah blah to do. Well, yeah, because look at this stupid language Java that they're trying to put in the first course there. Of course. So, and most of the studies don't reflect that, right? Because most of these studies are single trial studies. They don't look at the teacher's learning curve over multiple years and stuff like that. So I claim that and I think you would agree that we don't completely understand what's going on.
Oh, completely. Agreed.
Because there are too many artifacts from the side, including the dumb programming languages, including most computer people won't sit down and do a decent language for beginners. And on the other hand, most colleges will not accept languages for beginners in early courses.
I think that's a huge issue.
Right? Because they're worried about downstream, and so if we're going to use Java downstream as a senior, you've got to learn it as a freshman. That's just crap.
So I think I completely agree that the Advanced Placement in Computer Science is not what Alan Perlis wanted, and it's not a great course. On the other hand, in some sense, it's orthogonal to our problems. All right? There aren't any computer science teachers out there. Why? It's not because they don't like the course or they don't like Java. For the most part, they don't know it exists. Most of the students don't know that it exists. It's not in most schools. Now, I completely agree that a path to success would be to come up with a good programming language and a good course and to get it taught everywhere. However, a lot of the issues that we're pointing out here, those are issues no matter what the language is and no matter what the kind of course is. So for example, our pedagogy of computer science, getting working professionals to be able to learn computer science by whacking in front of, just fighting the IDE for hours and hours and hours, that's not going to work. We have to think of new pedagogy. The issues about why are high school students not being interested in computer science. I mean, in general, okay, APCS is not great. In general, though, the APCS is much more predictive of students taking further computer science courses than almost any other AP. Most students who take AP in statistics will never take another statistics course. Most students who take the AP in computer science will take more computer science courses. Okay, so I think the real issue is we need some computer science in high school. How do we get there, and how do we train teachers who are working professionals? This is a real problem. Yes, sir.
So just I was going on the idea of emotion, and you're getting these great results from media computation. We use our three of our C's today: the creativity, communication, and collaboration. Are you able to sort of discern what draws people into this? What gets them fascinated? Is it that they want to collaborate with other people, or do they want to create on their own, or do they want to communicate their idea that's creative?
It's a great question, and we have not studied that over time, so all I can really give you is anecdotal. When I started teaching the course, the media computation course, a lot of those C's were there. So for example, the media that I showed you, those were shared by the students in a wiki. So we actually used the Swiki, our Squeak wiki, and students would share their creations, their movies, their sounds, their images with other students. And what I would do as a teacher that was really fun is that before each lecture, so they'd work on it for about a week, so it'd be 3 or 4 lectures during that time, as I'd go to that page and start the lecture by saying, oh, that one's really great. Who did that? You did? How did you do that? And now I've got freshmen talking to other freshmen about how they're writing code and how they're achieving particularly interesting results. That was really great. I love that context. I don't actually teach that course anymore. It's become institutionalized. It's been given to our instructors, and I'm actually not allowed to teach it. It's disappointing, but nonetheless, institutionalizing something, making it happen regularly is a good thing. It's being sustained. They don't do sharing in the wiki anymore, okay? But it still hasn't had a drop in success rates. Now, I will bet the climate and culture of the class has changed, but I don't know in what ways. I haven't measured it. So I don't think that collaborative aspect of it, though I think it's powerful, I don't think it's critical to get people drawn in. I do believe, I'm going to bet, that the creativity aspect of it is critical. Because even today, it's actually easier for the teachers to say, okay, do this assignment, and I don't care what media you use. Whatever pictures, whatever sounds, whatever video you want to manipulate, just go do it. And the students love that. And so they produce really interesting things. And we do know the students show one another their artwork. You know, even in the classroom where they don't have the galleries anymore, they don't post them up, they still show one another. It's still an aspect of it. I created something really cool in my computer science class, which is, wow, that's a great thing to have people saying.
So if an individual says that, I created something, what about the collaboration aspect? Do they seem, is there still a draw to use ideas and build new things?
I don't know. I don't know. And it's actually, what little data that I have on that, because since I'm not currently teaching the class anymore, it's not, we don't have funding to continue studying that course. What little data I have gets confounded by the fact that it's a 300 student a semester course. So for example, the collage assignment. We used the collage assignment semester after semester after semester until we started finding that some collages looked shockingly similar to the collages from last semester. And did you know that those students happen to all belong to the same fraternity or sorority? Cheating happens. Students try to find shortcuts, and so that gets in the way of trying to evaluate what was the real value of collaboration. Alan.
So Matthew, people are interested in this. John Maloney, who I think it was the main Scratch guy. First, Scratch has more than 2 million things on its website that have been done by people using a kind of a social media model that's worthwhile. So while universities are doing other kinds of things, Scratch has been spreading around the world for a lot of internal reasons, because nobody's forcing anybody to do it. But they had a master's student recently do a web page that will show the evolution of when somebody puts out an interesting project. It will show, here's a project that somebody derived from this one. They started with this one and did this, and here's when it comes out as a kind of a systems diagram that shows you. And it's not exactly the same as collaboration, but it is basically using the work of others, which of course is what we do out in the real world, but what schools hate, because it messes up the way they try and assess people. And so you have this other thing where big projects in computing are really done by a single person, and that is a difficult one to pull off, especially in introductory classes. So I wanted to ask you one other question,
Sure.
which is, this has come up on your website, and it seems critical in a couple of dimensions to me, and that is, gee, high school is already full of courses.
Right.
And this has been a huge problem of, well, here's another subject, and admittedly, blah, 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 and all this and that, but where do we put it? And we go back to Curlis again and say, wow, computer science is not the only place that deals with processes.
Absolutely.
It's actually providing a kind of a language and a way of modeling processes, but there are processes in physics, there are processes in chemistry and biology, and the social sciences. Why don't we think of this as being something like the way math, like if they taught decent math, they would be using those, and they do a little bit in physics.
Right.
But if you think about it, now instead of having the stovepipes of the separate subjects, you could take a more integrated approach and say, hey, the subject we most not teach in high school that's important is systems. Systems and process, nonlinear feedback mechanisms. That's what's screwing the world right now, and mostly because most adults don't understand it. Why don't we get on that? And then we know just exactly what computers are for there and how we should actually teach it.
Right.
We can amortize it over almost all the other subjects.
Right. I feel like we're sort of playing out our blog discussions for the audience, but I completely agree. So in his lecture, Alan Perlis actually gives this great example of it was the business department, but they were doing economic simulations in 1961 at Carnegie Tech. And he talks about how it changes the field of economics. He says, in general, back then, economics was not an experimental science. Hey, let's devalue the dollar tomorrow and see what happens. In general, I mean, maybe that is happening, I don't know. But in general, economics was not experimental, but once you have simulations, you can. And they were doing simulations of businesses and organizations and whole national economies. And it's a really powerful and wonderful idea. So I completely agree that what Perlis wanted to see was it integrated into other subjects, such as economics. Teaching systems, I think, makes a lot of sense. Now, then you get back into these politics. So in general, the Computer Science Teachers Association has been hesitant, they actually not wanted to push the idea of teaching computer science in science and mathematics and business classes and economics, because their challenge is getting in enough high school computer science teachers, let alone teaching computer science to absolutely every high school teacher. There's a concern that that's somewhat short-sighted, but this is the end goal, that you want everybody to be using computer science as a form of literacy, as a medium. But I do understand their challenges. The CS10K is a huge goal. How do we go from 2,000 to 8,000 teachers over the next few years? And I should also, people may not realize, those 2,000 AP computer science teachers, depending on how you count, charter schools, private schools, etc., there are 25 to 30,000 high schools in the United States. 2,000 AP computer science teachers for 30,000 high schools. All right? The odds of hitting a AP computer science teacher to take out a particular high school is highly unlikely. There's just not enough out there. So no matter how you slice it, whether our issues are just computer science teachers or teaching computer science to all teachers, we have a huge problem with thinking about how do we teach all these adult professionals about computer science. Judy, you had a question.
Well, having listened to this conversation and pondered it ourselves in Australia, I just wonder whether we need to think outside the box and do something different, like starting to do something online at universities. Provide the stuff the teachers can't do, so that what a teacher isn't doing in a school can still be a lot of facilitation. But we do have online, we can do online grading or something. I don't know how you can find this stuff.
Right.
It's not as if this is one state in the US that you've got a problem and you think, hey, we can solve that, but it seems to be everywhere.
Yep.
Maybe someone else in the world is doing differently. So maybe we need to go outside the normal school model. I mean, it's great that you can try and teach teachers because we just know that that's not going to be solved by the
So one great resource in the United Kingdom is the Open University. And this actually has a physical presence, it has a campus, you can go there every day if you love. But all of their coursework is also transmitted. It used to be on BBC Two overnight, so you had a VCR and you would record your lectures overnight and then watch them when you had a chance. So it was partly students on campus, but mainly correspondence courses for working people to advance themselves academically. I enjoyed when I was growing up watching some of those university televisions enormously. And there is a more up-to-date initiative called Open Courseware, which is collecting from a number of universities around the world courses on individual lectures that are free for you to go and watch. So this could be a start.
So let me address both of these issues, please. So first of all, the Open University, I completely agreed, and I don't know if you're familiar, they now have a new introductory course, My Digital Life, which is actually based in Scratch. Students program in Scratch. They also program the external Scratch boards. So yes, the Open University is probably the best distance online education available. However, even they, I gave a similar, I talked about these issues when I was at Atixi in Darmstadt this last summer. They don't know how to teach the teachers either. I mean, they know how to do a particular course, but talk about a sequence of courses to achieve a particular degree. Particular high school teachers, teaching teachers is a really challenging space. And they don't have an answer yet, though I do agree that they offer models that we should be thinking about. I think that the most interesting thing that's happened in the last few weeks with regards to, so first of all, yes, it's a problem for absolutely everybody. I had long discussions with the Israelis, for example, who have exactly these issues. And there they have computer science integrated much more deeply into the high school, and they still have problems with generating enough high school teachers to teach that computer science content. There's all kinds of really fascinating issues that come up, such as one of them we were talking about yesterday. A teacher who was a really good computer science teacher in high school can make a lot more money if they leave the high school, right? Because there's a huge market for people who know something about computer science. But the most interesting advance along these ways is, in the recent past, is just this last week, the Royal Society, once headed by Isaac Newton, has just come out with a report calling for a revision of computing in the UK schools. That they want real computer science. They want to completely get rid of the current ICT curriculum, which is mostly about how to use application software, and they want to have a real digital media, computer science, and information technology curricula. What's particularly interesting is that the government responded the day before the report came out and said the ICT curriculum is defunct as of September, and we are developing whole new curricula. Now, I don't think they'll succeed. Right? We haven't figured out how to generate all those teachers. They don't have any more teachers than anybody else do. And so to say in September we're going to generate a whole new curriculum, and between now and September you're going to teach enough teachers to be able to teach that new curriculum, it's a huge issue. On the other hand, I don't know of any other country that's shown that political will to say, yeah, we're going to start there. We're going to scrap our existing curriculum, and we need a whole new rigorous curriculum. So I'm very excited about that. But there's all kinds of research issues in how to make this actually work. So the idea of having the universities do it online and I mean, in some sense, that's what the Stanford online courses are about, the machine learning and AI courses that they offered in database. Could we do this down to the intro level? Could we help teachers also understand the pedagogical issues? I mean, one of the challenges of teaching teachers, but also one of the hooks that you have, is that teachers want to understand, well, Sally has this problem. How do you help Sally? Right? And this whole idea of diagnosing a problem, it puts them in a metacognitive stance to start with, that they're all about looking at a problem and saying, how do I teach this better? How do I learn it better? But that's really hard stuff to teach. We don't know enough about pedagogical content knowledge, how to teach computer science as computer science, not as general education stuff. So lots and lots of work to be done in this space. But I agree with all of those issues that you're raising. Yes, Alan.
Well, I think, so my experience with teachers over the years is nobody works harder.
Agreed.
Nobody works longer, and the amount of what you might call quiet brain time to learn this, I don't think it doesn't, in a way, it doesn't take that long to learn this stuff, but it is really hard in the presence of noise.
Agreed.
Called the rest of life.
Mm-hmm.
So what the teachers can't do is get on an ocean cruise, or we've been using the bus metaphor. Get on a bus and be on it for 3 months, and nobody can do anything to you. So you can do anything you want while you're on the bus. And so one of the things that's interesting is Perlis's pronouncements are 51 years old now.
Mm-hmm.
And that's probably the average age of teachers in the United States is less than that. And so, if you look at it, this is really a political problem, because there's been plenty of time to grow teachers who understand science, and plenty of time to grow teachers who understand math. But the time for them to learn the epistemological stuff is much more fruitful when they're young than trying to tack it onto a busy adult at the end. They can do it, but the noisy part of it, I think, really goes against it. So these attempts to reform things in a few years are not nearly as good as finding a way to make a 25-year plan and just carry it out through one administration or another. I think this is the big failure of our system and most political systems. is that they just can't do a sustained plan through all the different political changes just because the plan is a good idea.
Mm-hmm. Mm-hmm. Yes, sir.
I have a 13-year-old son, and when I look at him and his friends, no surprise, they spend a lot of time playing video.
Right.
And when I look at some of them are just, they seem to me utterly worthless, but some of them, like at some point, World of Warcraft, Minecraft, they actually involve a lot of, as kids really get into them, they involve a lot of algorithmic thinking and processes. They start to program to build things, and they're already immersed in them. But so it seems like it's possibly an avenue, but it's also a big problem because, for instance, to get him interested in actually programming, he can do only, starting at the beginning, he can do tiny little things and already it just doesn't compete with the experience. On the other hand, he doesn't make that connection between what he's doing, stuff that he actually enjoys doing, with actually thinking in a particular way that would actually get him started.
Mm-hmm.
Do you have any thoughts on
Yeah, so I want to tell it's not my story, but I'm on her committee, so I think I'm allowed to tell it. Betsy DeSalvo's dissertation work. It's really wonderful work. Okay, so a couple of starting points, data points that I think you'll all agree with, but are really pretty interesting to think about. A lot of computer scientists today, particularly young ones, you ask them what got you interested in technology, they'll say video games. I played a lot of video games, I was interested in how they worked, I got into them. The demographics that play the most video games in the United States are African American and Hispanic teenage boys. And they are the lowest percentage of people in computer science programs. Kind of a weird problem. So Betsy DeSalvo was at the Learning Research and Development Center in Pittsburgh and decided to explore this problem. And so she started following around a group of African American boys who were taking this after-school program and watched how they played video games and talked to them about it. They don't see them as algorithms. They see them as training. They see them as life preparation. She actually had one student say, well, it's raining today, so I can't go out and play basketball, so I'll play it on the video game instead. It's the same thing. A big insight. African American boys never use cheats or mods, at least the ones that she studied. Okay? White boys always use cheats and mods. I mean, there's huge websites. They're constantly looking for what's the cheat to get to the next level. If you don't think about it in terms of cheats and mods, you don't think about it as something to modify. So how do we get these kids to think about it in a new way? So what she did is she developed this project called Glitch. Betsy went to Electronic Arts and took their game testing training. She hires African American teen boys to be game testers. She trains them. They get paid for what they're doing. They really do contract game testing for game studios in the Atlanta area. The numbers are astounding. I'm not going to get them exactly right, but of the only 2 of the 15 kids in her first cohort that originally said they were interested in going into computer science, 10 of them are now in computer science programs somewhere. Okay, 10 of 15 is a remarkable number when we're talking about African American teen men. And so by putting them in a game testing perspective, they all want to play the latest and greatest games. I mean, that's just really cool. But being a game tester means you have to think below the surface. You have to figure out what's wrong and then be able to describe it to the programmer. So it's just brilliant work. She's currently finishing her dissertation. For those who are hiring, yes, she's on the market, and yes, we've made her an offer already, and we're trying to keep her. Yeah, I think that it's really interesting work. And actually, one of the things that she says is that one of the biggest parts of it, the game testing is critical for get them to think below the surface. But a big part about it is she paid them, and that gave it value to their communities, to their families, and so that was a huge deal for them. And so that made that kept them in the program. That led to the retention that she had. Yes, sir.
So in music, we have a similar problem in that so many of the audio tools and composing tools have made it so widely available and easily accessible. We end up with a suboptimal local team. There's 25 million people who create music that is a two-bar loop of someone else's music.
Yeah.
and they all think of themselves as me, but we need to shove them off that
Mhm.
to the other side.
Mhm.
This is a really nice example of, going beneath the surface.
Yes. Yeah.
And once they get, I've seen it happen, that once they get a little taste of, now I've got to build my website for my beats,
Mhm.
I'm actually better off if I can customize it. And they start getting into a little bit of programming. But there are many people who get stuck on that shoal and can't
Yeah.
seem to get over to the other side of what's really possible. So,
And actually, there's another interesting story in Glitch, too, that connects to this, the going beyond, that also connects to Alan's comments about APCS. So Betsy tried to teach them APCS. She thought it would be a really interesting outcome to see how would they do on the APCS test. She couldn't get them to take the test. They weren't interested. And there's all kinds of other issues that were going on there about notions of self-efficacy. What happens if I don't do well? What does that mean? And there are also really interesting issues that some of the data that I found fascinating about is these are if they go to college, they'll be the first in their family to go to college. And their understanding of computer science. She had one interview with one of the kids who said, I now want to get a PhD in computer science. And that's where I'm going to go right after I get my degree from DeVry. And they didn't see any problem with getting a 2-year degree DeVry leading to a PhD. Because, well, that's not part of their family. It's not part of their story. But how does one get a PhD in computer science? Kim, yeah, you've been trying to word it.
But I think another problem we're seeing here is this is a problem of transfer.
Mm-hmm.
Real learning and real education is when the learner can make that leap and that transfer. That's the magic moment, right? Now, Jerome Bruner simplified it all. He says you have to just tell the student. You have to point it out. So if you see your son, making a tiny little script in World of War, you just tell him, hey, guess what? Guess what you're doing. I mean, that I think is the role of a teacher in any capacity, whether they're in a classroom, an off living room, an older brother,
a parent.
In a studio. You just have to point it out because that's the toughest part, I think. And there could be this big light and go, oh, my God,
You do have to point it out. I totally agree. It's just that the light bulb doesn't
always.
So one side comment on what you brought up, though. So humans have been on the planet for about 200,000 years, and this came up through geoscience 400 years ago. And one way of interpreting that, which is the way anthropologists do it, is that we're evolved to survive, and particularly to survive against quick-moving danger. So none of that has much to do with slow thinking, devious thinking, finding cases so you can use contradiction reasoning. All of those things that just were invented 2,000 years ago. So one thing that Mark has to mention, I think is key, that modern education is primarily about teaching things that our nervous system are not intrinsically set up to learn, but we can learn them. And so I once asked audiences, is calculus cheating? Because it's an incredible shortcut to dealing with things that the greatest genius of antiquity thinking about it. And I don't think calculus is cheating. I think calculus invented just recently and learned laboriously by us gives us something like a little extra piece of brain that people didn't have 100,000 years ago. And we literally think about the world differently than it does. And this is the problem with thinking about video games. Video games taste like something that any cave child would recognize 100,000 years ago. And science and math do not taste that. Most computing does not taste that.
Although if you think about reading, even readable languages compared to computer languages, I mean, I think one of the problems is that language has had, a few thousand years. I mean, it's very much designed for humans to recognize. It's had a lot of time to develop into something that humans can learn fairly easily. Computer languages.
No, we're wired for learning languages, but we're not wired for reading. So the difficulty people have with reading and why they'll abandon reading as soon as electronic media comes in television is causing people to flee from things that they used to do in order to go across time. The fact that the reading system that we have is one-to-one to the language that we learn to speak,
I'm
and
talking
it's
about
still difficult,
Yeah.
makes my point, not yours.
No, but what I'm talking about, I can't remember the research, but it's basically a study of all written languages have a certain ratio of parts to bigger parts that actually does match what we evolved for, so that we recognize parts and wholes, in letters, words, phrases, paragraphs, very much the way we apprehend natural words.
Yeah, and it's still difficult to learn, so that's...
Not as difficult, but most of us learn it, whereas most of us don't learn it.
So this gentleman here had a question, and then Lori.
Yeah, talking about at the college level, it seems like, there's almost an unwillingness to deal with the karma of having done it maybe in an ineffective way and created adults that don't get it, and young adults that don't get it, and then trying to figure out how to jam it all in a semester or a year. So what I'm interested in is how this connects, or what's being done with the younger children, because the other thing is that if you do what Papert did, then you don't have this massive problem of creating teachers that have to have it on the college level, because in his model, the teachers were learning it along with the children, and there wasn't this authoritative professor that had to be created before you could get started. And then those people grow up getting it and be making the policies, and will kind of go full circle.
Right, so I don't have a lot of data about young children. If my other half was here, Barbara does more with those levels. And she has been, all right, it's my wife, but I'm allowed to say it, really brilliant in thinking about some of these sorts of issues. So, for example, we have all these teacher professional development workshops where we teach teachers about the computer science. But just as Alan was saying, schools are not the best place to learn, which is a weird way of putting it, but particularly for the teachers. So she hires a lot of those teachers to then run her summer camps. The summer camp is this informal setting where you get to play with the same media that maybe later on you're going to be teaching in your classroom. And this gives the teachers to learn along with the students, but not in school. It's so hard to do in school. But summer camp is a great place. And so Barbara's thought about these sorts of hooks so that the teachers, and they're looking for someplace, a job they can get paid for the summer and go play with the stuff that I might later on use in my class. Yeah. So I completely agree with the Papert vision is where we want to get to. How do we get there? What's the first step? I think that's one of the things that Barbara is figuring out. How to set it up so that the teachers can have that opportunity to learn along with the kids, but probably outside of the traditional formal setting.
So it's wonderful that in this room we have one of the most experienced teachers ever at teaching children how to program.
BJ.
BJ, talk to us.
Actually, I found,
You taught Logo, you taught HyperCard, you taught eToys, you taught Stage Cats.
this
Playground.
But really, I think what I found as a teacher that was most important is you do have to learn it as the child. You have to put yourself in the position of the child when you're learning it. And I would think on the secondary level, you have to do the same thing. What are the pitfalls? And know it well enough so that I can help them through the pitfalls and be able to say to them, I know exactly what you're talking about. I made the same mistake, and here is one way of solving it. Can you come up with another way of solving it? But you do have to know it well enough that you're, one, not afraid to say, you know what, I don't know the answer. Let's work it out together. And then that puts me in the position of being a learner. And I have always believed that teachers are lifelong learners. You never stop learning. And in this arena with technology, you have to be willing to put in the time and the effort to know it, but not be afraid to jump in even if you're not considered a genius at that particular program you're trying to teach.
Lori.
Actually, I have a comment on that, and then I wanted to finish up with a question, though. But before BJ started talking, I was thinking with Alan, what you guys are saying is that from observation, when we were working with the open school, BJ was unique. There were 80% of teachers that were afraid to say to a student or hesitant or not confident enough to say, I don't understand it, let me go with you. And that was a problem.
Yep.
And that was not what I was going to say. So I'm going to go back full circle to you wanted to help people create through computing. And that not all of us are wired, and some of us are like a little later in life, and do want to create through computing. Programming scares the crap out of me. I look at it, I don't have patience. Somebody tried to get me to stand in the room one day and close my eyes and draw a circle. I'm like, I did it. Okay, PFD. I mean, it really didn't get me. Then they came out with things like HyperCard.
Right.
We were talking last
Yeah,
night that
I love HyperCard.
I could finally create something. I understood it, I could see it, I'm very visual, and I could make things that were useful to me. And those things, up until our conversation last night, I thought had vanished from the face of the earth. When you're teaching liberal arts, these students that you're talking about, and I understand you want them to get to think, and understand, but do you also share with them things that they can go and do later on that help things that, the things you're telling me, like the new supertargeting, hypertext, things like that, so that even though, yes, we want them to get a deeper understanding, I get all that behind it, but then also just useful tools that some of, I don't have, I'm not going to go out and learn right now.
Yeah.
I never had the interest.
When I teach it, I do talk about some of those sorts of things, but not all the people who teach those classes do. And it's sort of a shame that we're such a young field and have already become so ossified in so many different ways. I was, the first time we did the Python Media Computation Libraries, the index for all pixels and sounds started with 1, not 0. And I took such grief from so many people. Oh, no, all indices start with 0. I said, only since C, all reasonable things start with 1 because most human beings start counting with 1. You know, we have this, but you know, that's, computer science has decided C was right. 0 is where we start. So the second and third editions of the Python book, we start with 0. You know, you have to pick your battles, right? Every parent knows this, right? You pick your battles, which ones you're going to fight with, which ones you aren't. But you're, so I mean, I love the issue that you're raising is really near and dear to my heart. That we think about, we need different kinds of representations. We want to have people be aware of these really interesting, deep ideas and cultural ideas. So one of the things I'm really excited about at Georgia Tech is we have, it's not new now, we're 6 or 7 years into it now, a bachelor's degree in computational media. It is joint between the School of Liberal Arts and the College of Computing. Now, it did not come about because of the media computation class. It came about, as all undergraduate programs do, because there were a bunch of people already doing research together and they said, hey, we could build an undergraduate degree. However, I do like to believe that the media computation class enabled it, because no liberal arts faculty would talk about having a joint degree with computer science when over 50% of their students were flunking out of that subject every semester. And that is a really wonderful degree program. One of the classes in particular that the liberal arts side built, Ian Bogos designed this class. It's an introduction to computational media, where they learn 6502 assembler. They learn Chef. Does anybody in here know the programming language Chef? No? Okay. It is a programming language which does nothing but spit out pieces of text. But it is of the form of a recipe. All well-formed programs in Chef are a recipe. 1 cup of this, 2 cups of that, and then when it processes, it spits out text. They learn 5 different languages like this. They learn processing, they learn Chef, they learn 6502 assembler, I forget the other 2. But it's all about what should the language look like? What should you be able to do with the language? And that sort of thinking, it's really a shame that we don't ever talk about those things in computer science anymore. We have to create new degree programs to have these really deep and important discussions about communication as a form, computing as a medium. And so, yeah, we need to have that more. I now direct the computational media program, so I'm particularly excited about it. But I think that we sometimes have to do that. Alan's talked about that sometimes how many different biology programs do most schools have now, that sometimes it's the way you make progress is you go split off and start in a new direction.
Yeah, UCLA has over 25, not counting the medical ones.
Right.
These are the whole departments, the department heads of biology, and they have 9 different departments of medicine. They have 1 department of computer science. Guess how easy, but of course Georgia Tech has how many departments of computer science? You have probably 4.
Well, we have a college computing with 3 different schools now. School of Computer Science, School of Interactive Computing, and School of Computational Science and Engineering.
Did all of these departments just because they couldn't get the one they were in to move, and they wanted to do something new, and the reviewers hadn't learned how to review the papers, so they had to create a new field. And computing hasn't really done that. It hasn't created a new field over and over again. So the academic part of the thing has sort of gotten ossified, like you said, into a set of orthodoxies, most of which are completely irrelevant, were always completely irrelevant, and they certainly are now. And so that's a real problem. But, you know, this is also partly NSF's problem, because NSF has been urged to do what they do for the biologists, which is to fund new departments. And only the major places like Carnegie, Georgia Tech, and MIT have been able to pull it off with the funders.
I think computer scientists tend to think for computer scientists too, so this goes back to your 30-minute semicolon as well. Most of the tools we build are, even if they don't have one, implicitly a user interface, and we don't do enough thinking about user interface.
Completely agreed. Yep.
But unfortunately, we have to wrap up this fascinating. Maybe the panel can continue some of these ideas on Friday. Thank you very much indeed to
pleasure.
Laura and Alex.